Okay, so next section, section 3, which is definite integrals and their antiderivatives. So now we're starting to look at more of the rules with integration, okay? So first off, it's the order of integration. So basically, usually this is our upper limit and this is our lower limit. And the idea is the order of integration, if you wanted to switch out your upper and lower limit, you can do that if it makes it easier to solve, and all you have to do is change your integral to a negative. So instead of the upper limit being a, we're going to be b, and then a and f of x dx. And once we start doing these examples, you'll see why that's a little bit important. Alright, next up is the zero. The idea is any integral from a to a is going to be 0. So if you look at a graph, and here's our graph, and here's a, the integral from here to here, there's no area of a line, so the area under the curve at the same x value is going to be 0. Okay? Constant multiple. So the idea here, whenever you are trying to integrate a function and there's a constant in front, it's easier sometimes to remove the constant outside of the integral, so that way you don't have to worry about finding its antiderivative and continuing with just the function itself. So take out the k. And then the final thing is you will multiply your answer from the integral by k. That will be the final step. Alright, sum and difference. So the idea here is if you are taking the integral of two functions that are either added or subtracted, sometimes it's going to be easier to separate these into two individual integrals. And it doesn't matter if it's addition or subtraction, this is going to be the same thing. The limits don't change, the bounds, don't change, and you just separate f of x dx, so you find the integral of f of x, plus or minus, depending on, if it's sum or difference type of problem, the integral from a to b of g of x dx. So sometimes it's going to be easier to split these guys up, okay, and find the integral, the antiderivatives separately. Last rule is additivity, and the idea here is if you have one function from a to b, and then that same function you're asking for the integral from b to c. So for example, it's the same exact function. So if this is our function right here, and here's a, and here's b, and then here's c. So this function right here says, what is the area under the curve from a to b? And this function right here says, what is the area under the curve from b to c? I think we can see that since it's the same exact function, basically what we can do is combine these two, and instead of finding two individual areas, we can say, what is the area under the curve from a to c of f of x dx. Okay? Oh, and you guys didn't see where I was graphing, but this is what I was explaining. So from a to b, the area under the curve, from b to c, the area under the curve, and instead of doing two individual ones, we can integrate the whole entire thing. Alright, max, min inequality. If the max function and the min function are the max and min values of the function on a closed interval from a to b, then the minimum of f times b minus a is going to be less than or equal to the function, the integral of the function from b to a, which is less than the max of the function f times b minus a. and we'll do an example of that in just a second, okay? Actually, probably not in this video. We'll do an example from the homework in class together. Alright, so let's use these basic properties to do these problems. So suppose f and h are continuous functions, and they tell us a few things. They tell us that the function f of x from 1 to 9, the integral, is -1. From 7 to 9 of f of x, it's 5. And from 7 to 9 of h of x dx is 4. So using these three pieces of information, can we use the properties that we just talked about and identify these values? So here's the idea. Over here we have a constant. So what I can do is use the constant multiple, which says that I can pull out that constant outside of my integral. And now I just need to figure out what is the integral from 1 to 9 of f of x dx. So I'm going to use the example that they gave us, and it says the integral from 1 to 9 of f of x dx is -2. So now it's just going to be -2 times this equals -1. So my answer is going to be 3. Oh, 2, sorry. I added instead of multiplied, my bad. Alright, next. So here it says, what is the function, what is the integral from 7 to 9 of f of x plus h of x? So what we could do right now is separate these two using the sum property of integrals. So I'm going to separate this 7 to 9 of f of x dx plus 7 to 9 of h of x dx. And based on what they gave us up here, from 7 to 9, the integral of f of x is 5 plus the integral of 7 to 9 of h of x is 4. So total 9. Next one. Now, what do you notice here? It's f of x, there's 1 and a 9, but what do you notice is that the 1 and the 9 have been switched. Their bounds, their order of integration is different. So the order of integration is different. So if it was 1 to 9 of f of x dx, we know that that is -1. But if you flip-flop 9 to 1 of f of x dx, what does it say we need to do? The order of integration rule says that if you flip-flop, the only thing that changes is that integral value becomes the opposite. So f of x here is going to be -1, which is 1. Okay? Alright, let's look at the next example. Suppose h is continuous and h of r dr is 2. The integral of h of r from -1 to 1 is 2, and the integral from -1 to 3 of h of r is 6. So how can we find from 1 to 3? So this is definitely going to be an exam question. I've seen this multiple times. Okay? So it's important to use these properties and figure out how are we going to manipulate the properties to figure out this. So take a second, see if you can figure it out. I mean, you can kind of see where 1 and 3 are, but there's a few things that you need to do. So first of all, we need the lower bound to be 1. And the only way to get the lower bound here to be 1 is to flip the order of integration. So if I flip the order of integration of h of r dr, this is going to become -2. And now if I take -1 to 3 of h of r dr, it's 6. So all I want to do is do what? You want from 1 to 3, right? So you want both of these. So based on the additivity, you want this part and this part. So what are we going to do to the two? We're going to add them. Okay? So it's going to be -2 plus 6, which is 4. Alright, and then this one right here, it's 1 to 3. So, I'm sorry, 3 to 1. So again, it's going to be the order of integration. Okay? So this side is fine. -1 to 1, which is h of r dr equals 2. And then this one right here, we need that 3 to be at the bottom. H of r dr is equal to, so by flipping the order of integration, what happens is that this becomes -6. Oh, and that's a -1. Now, we do have a little bit of a problem. Why? Because you can't go from -1 to 1 and then pick up at 3 to -1. So what do we have to do? Well, no, actually this is fine. Okay, so this is fine. The only difference is that we should have probably written this a little bit backwards because we want the lower one at the bottom. So we want from 3 to -1 of h of r plus from -1 to 1 of h of r. So that is going to be -6 plus 2, which is -4. Okay, so we should have put them backwards, but you can kind of see that it still works. The 3 is at the bottom and the 1 is at the top. Okay. So 3 basic integral rules. We've kind of already done this. Okay, we did this in the last section. If it's a constant, that means if you take the integral of c, you end up with cx from b to a, which is the same thing as saying c times b minus c times a. And then of course you can factor out a c and you end up with c times b minus a. If it's linear, remember you take the derivative of this, so it's x squared over 2 plus c from b to a, which ends up giving us b squared over 2 minus a squared over 2. And remember the c's cancel out because we are subtracting. And then if it's a polynomial, we remember that when you take the antiderivative, it's always going to be x to the n plus 1 over whatever that n plus 1 became. Excuse me, from b to a. So x is b to the n plus 1 over n plus 1 minus, oh, don't forget the c, but the c cancels out when we subtract, a to the n plus 1 over n plus 1. Alright, so these are 3 basic rules, and we've kind of used them already, but let's use them right here. So this right here is a linear function. So instead of actually figuring out the antiderivative or the integral and then plugging in, I'm going to use this rule right here, which says you take your b, and remember your b is your upper bound. So you take your b, you square it, divided by 2 minus your a, square it, divided by 2, and that is going to be your answer. So that's 25 over 2 minus 9 over 2, which gives us 14 over 2, and that's going to be 7. So this is an easy integral rule. Next up, this is a polynomial. So the idea is that if you take your b, now this is general, okay? So remember, you do have to take into account both. I don't recommend memorizing this. It's going to be a lot easier, I think, to just integrate this because we know how to integrate it. So this is just going to be 2x cubed over 3 minus 6x plus c from 2 to 0. I mean, you could take this and then, use it, but this only works for if there's only a single polynomial. You do have to take into account that 6 as well, so you do have to do it again. So I think this is easier. Alright, so this ends up being 2 times 2 cubed over 3 minus 6 times 2. The c's cancel out, and then this side is completely 0 because you plug in 0. So this ends up being 4 times 2 is 8 divided by 3 minus 12. And I'll let you guys figure this out because I don't feel like doing any fractions, and I don't have my calculator by me. Alright, so for the function y equals 3 minus 3x. Actually, let's do the integral and areas definitions first. So, if an integrable function, y equals f of x, has only positive y values on the interval, so if it's strictly a function that is in the positive y values, okay, so above, on the interval from a to b, then integrating the function gives a positive, it gives the area only. Okay, and it gives you only the positive values, the positive integral. Now, if y equals f of x has both positive and negative y values, then integration gives you the net area. So an example of that graph would look like this. So you have, let's say, from A to B. So you would have a portion well, I kind of graphed this wrong. So I would probably have to go like this. And let's call this A and this B. So we have an area below and we have an area above. That is going to be called the net area. If y equals f of x has both positive and negative values, and you are asked to find the total area, then you would need to find the absolute value of any area that falls below the x-axis, the negative area, and add it to the area under the curve that falls above the x-axis, the positive area. Here's the key, the absolute value, because you cannot have an area that is negative, correct? Alright, so let's do let's do example 4 right here. So for the function y equals 3 minus 3x squared on 0, 2, we're going to find the following. So I'm going to take a second and I'm just going to draw that over here. And I'm only going to focus on the interval 0 to 2. Okay? So at 0, my graph is at 3. At 1, it's going to be well, let's call this half because I want 1 to be right here. At 1, it's going to be add 0. And then, let's call that 1.5. And then at 2, it's going to be at negative 9. So this part of the graph looks like this. And I want to integrate this from 0 all the way to 2. And remember, when you're finding the area, your x-axis is always going to act as your base. Now, based on our rule, we know that because this is below, this is going to have a negative value, and this is going to have a positive value. But when we take the total area for part C, we're going to have to do the absolute. So, and for part A. Alright, so let's look at this example. So here's the graph. It's not going to be in the window when I'm doing the math, so deal with me. Alright, so step 1 is the total area. So the total area means that we need to separate the two. And the reason we need to separate the two areas is because, so this is going to be area 1 and this is going to be area 2, is because one is going to be positive and one is going to be our negative. Okay? So basically the idea is we are going to integrate from 0 to 1 of 3 minus 3x squared dx plus the integral from 1 to 2 of 3 minus 3x squared dx. And because this is saying the total area, I'm going to make sure that I take the absolute value of this. And why is it the absolute value of this one and not this one? Because this part is what's in the underneath. Okay? It's where the y values are negative. So evaluate this, which means find the integral. So this becomes 3x minus 3x cubed over 3, which is the same thing as x cubed, from 1 to 0, plus the absolute value of the same function, so 3x minus x cubed, from 2 to 1. And we're making sure that we take the absolute value of this. Alright, you do the math. Plug in 1 first. I'm going to ignore c just because I know it's going to get canceled out. So this is going to be 3 minus 1 minus 0 plus, this whole thing is going to be an absolute value, 6 minus 8 parentheses minus 3 minus 1. I'm making sure these are in absolute values. Keep going. So this becomes 3 minus 1, which is 2 minus 0 plus absolute value. 6 minus 8 is negative 2 minus 2 is negative 4. So this is just 2 plus 4, which is 6. So this is my total area. Now, what is the net area? The net area is going to be a little different here. The net area, we're going to integrate the whole entire thing, the net, okay, from 0 to 2 of 3 minus 3x squared dx. So when we integrate this, it's going to be 3x minus 3x cubed divided by 3, which ends up giving us x cubed. I'm going to ignore the plus c for now because it's defined, from 2 to 0. So now when we solve this, we're going to get 6 minus 8 minus, plug in 0, so we get negative 2. That is called the net area. So total area on the calculator and net area on the calculator, we'll look at these tomorrow in class together. Try to do them on your own, and there should be a key for it. I don't remember how to get to it exactly. Now, supplementary homework problem, repeat example 4 using the following function on 02. Include this in your homework. So the homework for this, the homework for section 3 is page 274, 1 through 31, odds. Obviously we did not complete section 3. This is only the first half of it. So you should be able to do the examples that deal with what we've done so far. So start those. There is only one more page left of section 3, but that's enough for one video. Okay, so remember, if you can do this part, you're good. And if you can do the examples like these, you're good. And we'll do one of these together in class tomorrow. All right, enjoy.